Today, we will talk about isomorphisms of vector spaces. The concept of isomorphism is ubiquitous in mathematics. It's a way to express the idea that two different objects are essentially the same. So we'll start with the definitions. So let f be a function between two sets. So f is defined on a set A and assumes values in a set B. So definition, we say that f is bijective if for every element B in the set B, there exists a unique element A in the set A such that f of A is equal to B. Pictorially, this can be expressed in the following way. So suppose we have some set A and another set B, and our function assigns to each element of the first set one element of the second set in such a way that it creates a one-to-one correspondence. And so this is another name for this word bijective, or so bijection is the same as one-to-one correspondence. And so what's important for us is that every element of the set B has a unique preimage, right? So this means that for each element in the second set, there is an arrow that goes to this element from the first set, and there is only one such arrow. So we don't have two elements of set A that are mapped to the same element of the set B. Now, let us see how this idea plays out in the context of vector spaces. Let V and W be two vector spaces over the same field F. Definition. A function T with domain V and assuming values in W is called an isomorphism of vector spaces if T is bijective. So this means that for each element of vector space W, there exists a unique preimage, and it satisfies two properties. One, for all vectors v1 and v2 in V, we have T of the sum v1 plus v2 is equal to T of v1 plus t of v2. And the second property, for every v in vector space V, and for every scalar c in the field F, t of c times v is equal to c times t of v. So if we have a bijective function between two vector spaces that satisfies these two relations, so basically these relations say that this function is compatible with the vector space structure, so then such a function is called an isomorphism. And we say that two vector spaces V and W are isomorphic if there exists an isomorphism T from V to W. Now let us point out one consequence of this definition. So if T is an isomorphism, so then this implies that T of a zero vector, so T transforms a zero vector into a zero vector in the space W. And to prove this, set the scalar to be 0 in this property 2, right? So because if we pick any vector, right? Or for example, we can even pick 0 vector, right? So we can take c equals 0 and v also to be 0, right? So we get 0 times 0 vector is equal to 0 times t of a 0 vector, right? And then on the left, we have t of a 0 vector, right? So if we multiply 0 vector by 0 scalar, we still have 0 vector. And on the right, if we have any vector and multiply it by 0 scalar, then we know that the result is a 0 vector. And so this shows that t transforms a 0 vector into a 0 vector. Let us look at some examples. So as the first example, so let us say that vector spaces M22 of F and F4 are isomorphic. Now, what are these spaces? So M22 of F, so these are 2 by 2 matrices with entries in F. And so F4, so this is a 4-component vectors with entries in the same field F. So let us construct an isomorphism between these two vector spaces. So we need to construct T from M22 of F to F4. And we define this in the following way. So if we have a matrix A, B, C, D, then we transform this vector, this matrix, into a vector with 4 columns, 4 components, A, B, C, and D. Now, So this is our function, our transformation. So here the input is a 2 by 2 matrix, and the output is a vector with 4 components. So what we need to show, so in order to prove that this is an isomorphism, we need to show 3 things. That this function is bijective, and it satisfies these 2 properties of an isomorphism of vector spaces. What is the bijective property means? So it means the following, that for every vector A, B, C, D in F4, there exists a unique matrix in M22 of F. Say, call this matrix A, such that T of A is equal to A, B, C, D. But this is obvious because by our definition, the only matrix that can be transformed into ABCD is the matrix ABCD like this, right? So it's clear that every vector in F4 has a unique preimage in the set of matrices over the field F. Now let us discuss compatibility with the vector space structure. What property 1 says in this context. So here we take arbitrary pair of matrices. So A1, which is A1, B1, C1, D1, and A2, which is A2, B2, C2, and D2. And what we need to show is that T of A1 plus A2 is equal to T of A1 plus T of A2. Now, to prove this equality, what we do is we compute the left-hand side and the right-hand side. And we show that the results are the same. So let's take the left-hand side. So here we have T of A1 plus A2. So this is T applied to a sum of 2 matrices, A1, B1, C1, D1, plus A2, B2, C2, D2. Now, how do we add 2 matrices? We add 2 matrices component-wise. So this is equal to T of the following sum of 2 matrices. We have A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2. And now we use our transformation. We know that a matrix is transformed into a column vector in this simple way. So this means that this matrix is going to be transformed in the following 4-component vector. We have A1 plus A2, B1 plus B2, C1 plus C2, and D1 plus D2. Now let us look at the right-hand side. So in the right-hand side here we have T of A1 plus T of A2. So this is T of the matrix A1, B1, C1, D1 plus T of the matrix A2, B2, C2, D2. Now, so our transformation transforms matrices into 4-component vectors. So the first matrix is transformed into vector A1, B1, C1, D1. And the second matrix is transformed into a four-component vector a2, b2, c2, d2. And now we add these two four-component vectors. And vectors are also added component-wise. So the result is going to be a1 plus a2, b1 plus b2, c1 plus c2, and d1 plus d2. And so what we see is that the result of computation of the left-hand side is exactly the same as the result of computation of the right-hand side. So this shows us that this property holds, right? So the second property I leave for you as an exercise. So kind of phrased in terms of matrices. So this will say that T of k times A is equal to k times T of A, right? So here it's better to use the scalar k instead of c, because we use c in here inside the matrix. All right, and so this is an exercise. So let me point out one detail in this definition and in this example. So here in the left-hand side, so this addition operation is carried out in the space V, whereas in the right-hand side, so the same addition is carried out in the space W. And here we essentially show that addition in V corresponds to addition in W when we apply transformation T. And so here in this example, we could see that here, this plus, we add two four-component vectors, whereas in this addition here, we add two matrices. Let's consider our second example. Here we say that the space of quadratic polynomials so let's call it V. It's the set of ax squared plus bx plus c, where a, b, and c belong to some field f. So this vector space is isomorphic to the space F3. And so to prove this, we construct an isomorphism. So we construct a map T from vector space V into F3. And clearly, the way to do it, so we define that a polynomial ax squared plus bx plus c is transformed into a three-component vector ABC. And so we need to show that T is an isomorphism, which incorporates three properties. So the first property, we need to show that it's bijective. And then two more properties is that it's compatible with the vector space structure. So bijective. So what does it mean? So this means that for every vector ABC in F3, there exists a unique quadratic polynomial P such that T of P is equal to ABC. But this property is obvious because by our definition of the transformation, it's clear that the only polynomial that goes to vector ABC is this one. It's ax squared plus bx plus c. And for every, so this means that every vector has a preimage, and this preimage is unique. So this means that this transformation is bijective. And now we check compatibility with vector space operations. So here we take two polynomials, P1, which is a1x squared plus b1x plus c1, and P2, which is a2x squared plus b2x plus c2. And we need to show, that T of P1 plus P2 is equal to T of P1 plus T of P2. Again, let us work out the left-hand side and the right-hand side. So for the left-hand side, we have T of P1 plus P2. So what is this? This is T applied to the sum of two polynomials, a1x squared plus b1x plus c1 plus a2x squared plus b2x plus c2. Now, let's add these two polynomials. So let's simplify this polynomial expression. That's T of a1 plus a2 x squared plus b1 plus b2 x plus c1 plus c2. And now let us check our definition of T. So transformation T transforms this polynomial in a three-component vector. So this means that this polynomial gets transformed into vector with first component a1 plus a2, the second component b1 plus b2, and the third component c1 plus c2. Now let us look at the right-hand side. In the right-hand side we have T of P1 plus T of P2. So that is T of the polynomial a1x squared plus b1x plus c1 plus T of the second polynomial a2x squared plus b2x plus c2. Now, the first polynomial is transformed into a three-component vector a1, b1, c1. And the second polynomial is transformed into a three-component vector a2, b2, c2. So when we add these vectors, we get a1 plus a2, b1 plus b2, c1 plus c2. And what we see is that we arrived at the same result as for the left-hand side. So what we see that right-hand side is equal to the left-hand side. And so this establishes this property here, right? So this is now established. And then there is the second property that I will leave as an exercise. We need to show that T of k times p, if we multiply a polynomial by the scalar, is the same as multiplying T of p by the same scalar. And so this I leave as an exercise for you. So as our next example, so let us show that the space of vectors on a Euclidean plane is isomorphic to R2. Right? So what we do here is we take Euclidean plane and we consider our vectors on Euclidean plane. Of course, with understanding that two vectors are equal if they form a parallelogram. And we define the operations of addition and multiplications of these vectors by a real number. So this means that the set of vectors on the Euclidean plane forms a vector space. So we are claiming that this vector space is isomorphic to R2. So let us prove this. So here, the first order of business is to construct the actual isomorphism between vectors on Euclidean plane and R2. And what we do is the following. So we consider an arbitrary triangle on a plane. So ABC. So we take any three points that are not on the same line, and we consider this triangle. So next, we consider two vectors. So A from B and from A to C. From our discussion of vectors on the Euclidean plane, we know that this pair of vectors, AB and AC, form a basis. Now we can construct our actual isomorphism between R2 and this space of vectors on Euclidean plane. Let's call this space V. And so we construct this transformation from R2 to V in the following way. So we take a vector from R2. It's a two-component vector with scalars in real numbers. And we transform this two-component vector into a linear combination of our basis vectors. So K1 times AB plus K2 times AC. So now we have our three things to prove. So we need to prove that it is bijective and that it is compatible with the vector space structure. Now, what bijectivity property mean? So it means that any vector from our Euclidean plane has a preimage, as a unique preimage as a two-component vector. Now, we know that any vector on this plane can be drawn with a starting point at A. So what we need to show is that for any vector AD in V, there exist K1 and K2 in real numbers, such that T of K1, K2 is equal to AD. But, so we know that our vectors AB and AC form a basis. And one of the properties of a basis is, so from properties of a basis, we have that every vector AD is a linear combination of our basis vectors AB and AC. So this means that there exist K1 and K2 in R. such that AD is equal to K1 times AB plus K2 times AC. But that is precisely T of K1, K2. So what we proved here is that every vector on this Euclidean plane has a preimage in R2. So to construct this preimage, we decompose any vector as a linear combination of AB and AC. And so the coefficients of this linear combination give us the vector in R2 that gets mapped into this vector AD. So this, however, is not enough for bijectivity, because we proved that any vector has a preimage in R2. But we also need to show that this preimage is unique. So unique preimage. So how do we prove this? So suppose some vector AD has two preimages. So it's T of K1, K2, but also it's T of another vector from R2, S1, S2. So we need to show that if we have this equality, then actually these two vectors must be the same. So what does it mean? So this means that this equality means that K1 times AB plus K2 times AC is equal to S1 times AB plus S2 times AC. Now, if we move everything to one side, so this will tell us that K1 minus S1 times AB plus K2 minus S2 times AC is equal to a zero vector. But again, we have that these two vectors form a basis. And we had our second property of a basis is that if a linear combination of two basis vectors is equal to the zero vector, then both coefficients of this linear combination must be zero. So in other words, well, our two properties of a basis here is that the first property is the spanning property, right? So this means that every vector AD is a linear combination of a basis vectors. And the second property is linear independence property, right? So from here, we conclude that K1 minus S1 is equal to 0. And K2 minus S2 is also equal to 0. And that means that K1 is equal to S1 and K2 is equal to S2. So these two vectors then are equal. So the vector K1, K2 is equal to vector S1, S2. So if we assume that two vectors from R2 get mapped to the same vector AD, so then this shows that these two vectors must be actually the same. And this tells us that every vector AD from the space V has a unique preimage in the space R2. So this means that indeed this transformation is bijective. Now let us investigate compatibility of this transformation with the operations of vector spaces. So here we need to show that T of the sum, so that the sum of two vectors is mapped to the sum of their images. And again, we verify this by computing the left-hand side and the right-hand side. So for the left-hand side, we have T of K1, K2 plus S1, S2 is T of, so we add these two vectors. So it's k1 plus s1, k2 plus s2. And then a two-component vector is mapped into a linear combination. So this is mapped to k1 plus s1 times ab plus k2 plus s2 times ac. Now let's compute the right-hand side. So for the right-hand side, we have t of k1, k2 plus t of s1, s2. So the first gets mapped to linear combination k1 ab plus k2 ac. And the second gets mapped to s1 ab plus s2 ac. And so this is equal to k1 plus s1 ab plus k2 plus s2 ac. And again, we see that the left-hand side is equal to the right-hand side. So this proves our second property of the isomorphism, and the last property I leave as an exercise. Right? So here we need to show that t of a constant times k1, k2 is equal to c times t of k1, k2. So this is an exercise. Now let us state the main theorem of today's lecture. Let V be a vector space over a field F of dimension n. Then V is isomorphic to the space Fn of n-component vectors with entries in F. So let's give a proof. So what we know, well, V is a finite dimensional vector space. So we know that an n-dimensional vector space has a basis with n vectors, v1 through vn. Now we fix this basis and we construct a map T from Fn to V in the following way. So we say that T of k1, k2, ... kn is equal to k1 v1 plus k2 v2 plus kn vn. So first of all, we need to show that T is bijective. What does it mean? So T is bijective means that for every vector u in V, there exists a unique vector w in Fn such that T of w is equal to u. If we want to prove that some property holds for every vector in V, then we do the following mental trick. So we say let U be an arbitrary vector in V. Now, if we can prove the property, whatever we need, for an arbitrary vector, this proves it for all vectors in the vector space. And so when we need to prove that something holds for all objects, then what we do instead is we prove that this property holds for an arbitrary object in our space. So what we have is we have a basis here, right? So we know that our set V1 through Vn spans V, right? So because a basis is a linearly independent subset that spans the vector space. So what does it mean that a set spans V? This means that an arbitrary vector can be written as a linear combination of basis vectors. So this tells us that there exist scalars C1 through Cn in F such that U is a linear combination C1 V1 plus Cn Vn. But that means, so this implies that T applied to the following n component vector C1, C2, Cn, which is this linear combination. So this is simply equal to U. And so this shows that, so we have a pre-image W for our vector U, right? So this, if we take this n component vector W, then T of W is equal to U. So this means that our arbitrary vector has a pre-image. Now we need to show that this pre-image is unique. So to prove this, so uniqueness. So to prove uniqueness, we make an assumption that two vectors are mapped to the same vector U. That U is T of C1 Cn, and also it is T of K1 Kn. Now, what this equality would mean? This equality, using our definition of T, means that C1 V1 plus ... Cn Vn is equal to K1 V1 plus ... Kn Vn. And again, let's bring everything to the left-hand side. So this implies that C1 minus K1 V1 plus Cn minus Kn Vn is equal to 0. But again, we recall that we have a basis, and the basis is linearly independent. So from linear independence, we know that if a linear combination of this set of vectors is equal to a 0 vector, then by definition of linear independence, all coefficients of these linear combinations must be equal to 0. So we have C1 minus K1 is equal to 0, and Cn minus Kn is also equal to 0. But then this means that C1 is equal to K1, and so on. Cn is equal to Kn. And so this implies that the vector C1 Cn is equal to the n-component vector K1 Kn. And we proved exactly what we had to prove. So we proved that any vector cannot have two distinct pre-images. So the pre-image of any vector exists. So this was our first step. And now we prove that not only it exists, but it's also unique. So next we verify compatibility of this map with the operations of our vector spaces. So here we need to prove that T of the sum of two vectors, so if we have k1 up to kn plus c1 up to cn, so this is equal to T of k1 up to kn plus T of c1 up to cn. And again, we compute the left-hand side and the right-hand side. So for the left-hand side, so if we add these two, we get T of k1 plus c1 up to kn plus cn. And so this gets transformed into linear combination k1 plus c1 v1 plus kn plus cn vn. But for the right-hand side, we have the T of k1 kn plus T of c1 cn. So that equals to k1 v1 plus kn vn plus c1 v1 plus cn vn. And what we get here, so taking the sum, we get k1 plus c1 v1 plus kn plus cn vn. And comparing these two, we see that the left-hand side is equal to the right-hand side. So this means that this property holds. And so the final property is left as an exercise, right? So, one needs to show that T of a constant times k1 kn is equal to C times T of k1 to kn. And that's an exercise. So now this completes the proof of this theorem. And basically, the takeaway from this theorem is that for finite dimensional vector spaces, two vector spaces are isomorphic if and only if they have the same dimension, because both of these vector spaces will be isomorphic to Fn. Now, the remaining part of this lecture will have nothing to do with linear algebra. So here I wanted to discuss the concept of isomorphism in a wider sense and play some games with you. So let's consider the following game. So let's take the following set of numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, so the game is like this. So two players, say red and blue, claim in turns numbers from this set. And once the number is claimed, then it goes into the sack of the player who claimed it, and it's removed from this set. And so to win the game, a player must claim 3 numbers that add up to 15. All right, so this is the game. Now let's try to play this game. Okay, so suppose so we have the pile of red here and another pile of blue. Okay, so suppose red goes first and claims 7. Right, so this means that now 7 is captured here. All right, so say blue goes second, and well, I don't know. Suppose blue claims 8. So now it's red's turn, and so suppose red is going to claim 3. Now, what's the blue's move? So blue cannot win right now, right? 7 plus 3 is 10. So if on the next move red claims 5, then red would win. So for this reason, blue has to claim 5. Right? So now, so red cannot claim 5. So this means that red cannot win on the next move. But let's look what happens with the blue. 8 plus 5, that's 13. So if blue claims 2, then blue will win the game. So this means that for the red not to lose, red must claim 2. All right. So now blue cannot win in the next move because we have 2 is already claimed. Now what happens with red? So let's see if blue can not lose. So there are the following pairs here. So 7, 3, that will require 5, but 5 is not available for red. 3 plus 2, that's 5, and 5 requires a 10, but 10 is not here. So this pair is also safe for blue. There is also 7 and 2. 7 and 2 is 9 together. So if red claims 6, then this will be 15. So this means that in order not to lose, blue must claim 6 here. All right. So now we can see that all red's moves, winning moves, are already blocked by blue. So let's see what happens if blue can win on the next move. So we have 8 plus 5, that's 13. Well, we already blocked this by claiming 2. 8 plus 6, that's 14. So this means that if blue captures 1, then blue will win. So this means that red must claim 1 here. But what do we have here? 5 plus 6 is 11, right? And 11 plus 4 is 15, right? So if blue claims 4, then blue wins, right? So because 5 plus 6 plus 4 is equal to 15, right? So blue claimed 3 numbers that add up to 15. Now I have a question to you. Have you ever played this game? If not, so I suggest that you kind of stop this video here and go and play this game with your friends and see if you can develop good strategies to play this game, and so just get some experience with this game. And think whether you have seen this game before or not, right? So now take your time. In the rest of this class, there is nothing that's going to be on the final exam. So play this game for a while and then come back and finish this video. All right, welcome back. So now that I got you back, so let me tell you that in fact every single person in this class have played this game many times, and you know everything about winning strategies in this game. But in order to realize this, so we need to see that this game is isomorphic to another game which everybody knows. And this other game is the game of tic-tac-toe. Right? And so if you know how to play tic-tac-toe, then you will know how to play this game. And so basically, so what I'm trying to say is that this game of picking three numbers that add up to 15 is isomorphic to the game of tic-tac-toe. But this isomorphism between these two games is not at all obvious. And to construct the isomorphism between these two games, we need something which is called a magic square. So what's a magic square? So a magic square is a 3 by 3 square filled with numbers from 1 to 9 that has the property that everything here adds up to 15 in each row and each column. Okay, so let's see. So here in this row, the sum is 15, so is here, and so is here. So then in columns, we have 15, 15, and 15. And also on the diagonals. So we have 15 on this diagonal and 15 on this diagonal, right? So this is called the magic square. So now I'm claiming that using the magic square, I can construct an isomorphism between tic-tac-toe and this game of 15.